welcome everybody to CCNA Scaling Networks version 6, chapter 3, Spanning Tree Protocol. Thankfully we have Spanning Tree. Spanning Tree is what gives us our redundancy at layer 2. So we've got a nice perfect triangle there between switch 1, 2 and 3, and they have negotiated. The Spanning Tree Protocol algorithm has run and has decided to block the port on Fast Ethernet 2 on switch 2, and therefore there's no longer a loop. The connection, when all the PC 1, 2 and 3 need to get to PC 4, they go up through switch 2 then onto switch 1. Now if for some reason the link between switch 2 and switch 1 fails, then after a few seconds switch 2 will realize that it can no longer see switch 1 and then begin to forward frames up towards switch 3 and then to switch 1 and then on to PC 4. So Spanning Tree algorithm is designed to reduce loops that occur at layer 2. It does this by giving all the links a cost. So there's a BPDU, a bridge protocol data unit, that moves between all the switches every few seconds, and that information has information about the ports and the speed, and also identifies the switch with a bridge identifier. It's a bit hard to see there, but you'll see that the bridge identifier is represented by a number here, or a priority value, and then this value here, the CCC, CCAA, BBB, these are the MAC addresses of the switch. So switch B has got a MAC address of all B's, switch A has got a MAC address of all A's, and switch C has got a MAC address of all A's. Now because they've still got 32,768 at the front, the tiebreaker is now the MAC address. So when a switch is turned on, identify the root bridge, BPDUs send out with the bridge identifier. By default, 32,678 is just glued onto the front of the base MAC address to give us the bridge ID. So switch A is the root bridge because it has the lowest MAC address, or the lowest bridge identifier. AAA is lower than B and C. Now the root bridge, this is one of these funky little rules. The root bridge, which is the middle of your spanning tree algorithm, will never block any ports. The root bridge will never block a port. So therefore the other switches now detected that there's a loop. So they have to take it upon themselves to block a port. Now on Cat B up the top, 1/2 is only running at 10 meg, whereas 1/1 is running at 100 meg. So therefore switch B has said, look, I've got two ways to get to the root, but the slower way, I'm going to block that. And that's because it actually costs more. Remember, cost is money. So a higher cost means not as better as the lower cost. Same here down here with Cat C. Cat C has got a 10 meg interface and a 100 meg interface. So the 100 meg interface has got a cost of 19, so that's cheaper than the cost of 100, so therefore the higher cost will be blocked. And by default, Cisco switches use PVST. So here we have one of my favorite examples. We've got two switches, top switch and the bottom switch. We've got port 1 to 8 and port 8 to 1. Now we're assuming there's a factory default, so the default priority. So as far as the root bridge election process goes, they got the same priority. So the MAC address is the tiebreaker for the election. So the top switch is 000A 1234 AAA, and the bottom switch is 0008 1234 BBBB. So therefore, mathematically, this MAC address of AAA is lower. So the top switch will be the root bridge. Now we know that the root bridge cannot block any of its ports. So therefore, one of these two ports on the bottom switch needs to be blocked. So the bottom switch has to decide which ports it's going to block. Little thing 2, so every 2 seconds, a BPDU is going to come out of the root bridge, come down to this bottom switch, and the bottom switch is going to have to make the decision of which port it is going to actually choose to block. So what do you think? actually going to be port 1 on the bottom switch. And you might think to yourself, Josh, that's crazy. What are you talking about? It's, port numbers and port costs and speeds and MAC addresses and all that sort of stuff. Why is it port 1 that's being blocked? Because port 1 is a lower number than 8. That is true. However, think about the communication. The top switch is the boss. It's sending out a BPDU, a bridge protocol data unit, every 2 seconds with all the information that the bottom switch needs. Part of that information is how to get to the root bridge. What have I been told is the best path to get to the root bridge? Port 1 says I'm port 1. Port 8 says I'm port 8. So the bottom switch receives this information and says, right, the most efficient path for me to get to the root bridge is to get to the root bridge on the root bridge's port 1. Therefore, port 8 on the bottom switch remains active and port 1 on the bottom switch shuts down. Now let's look at some specific terminology. The root bridge is the center of the spanning tree algorithm. Any port on a switch that's facing towards the root bridge is a root port. Any port on a switch that's facing towards the root bridge is a root port. Any port that's facing away from the root bridge is a designated port. So, see, this one's facing towards the root bridge, root port. This one's facing towards the root bridge, root port. These two ports are facing away from the root bridge, so therefore they're designated port. This port is facing away from the root bridge, so it's a designated port. Now this one must have the lowest MAC address, so therefore this one has become blocking, or alternatively. So, little rules of thumb to keep in your way. If you have a switch and any port at all on this switch is a root port, it is not the root bridge. If you're on the root bridge, all of your ports will be designated. Designated ports face away from the root bridge. The anatomy of the BPDUs. BPDUs have got protocols, version, length, flags, root ID, all that sort of funky stuff. But they also have the cost of the path, and that's a cumulative cost. They've got the bridge ID, and they've got the port ID. So it's all about the bridge priority and the MAC address making up the bridge ID, because the lowest bid will be the best path, because the root port is the best way, the most efficient way to get towards the root bridge. So let's do a little quick quiz to make sure we're all on the same page. If we've got a bridge priority of 32,768 and the MAC address of 112233344556, therefore that is our bid. 327681122334556. That's the bid. That's the bridge identifier. Now, the way we set the priority is pretty straightforward. Spanning tree, VLAN, and then the number of the VLAN, priority, and then a value. Now, the value size is 65,535, but Cisco in their infinite wisdom have said, no, that's too much variety. So we'll just give you 16 options. So they've divided that big value, that 2 bytes value, into 16 increments. So you do spanning tree VLAN 1 priority question mark, and they're your options. 0 up to 61,440. Whereas 32,768 is the exact middle. So that's the default, the midpoint. Now here's a little trick that isn't obvious, but we'll look at it. And there's a question in the exam on this, so it's important to notice. Spanning tree VLAN 1 root primary, spanning tree VLAN 1 root secondary. They're little friendly keywords for you. So you got a bunch of switches, they're all plugged in, they're all chatting. You go to the first switch and you say spanning tree VLAN 1 root primary. It automatically sets the priority for that VLAN to be 24,576. If you go to another switch and you say VLAN, spanning tree VLAN 1 root primary, then that switch will know, oh hang on a minute, there's already a boss who is 24,576. So I'm going to have to make mine less than that, 20,480. And then you go back to the first switch and you notice it's not the root primary anymore. So you do spanning tree VLAN 1 root primary, and it will detect that there's a current root that's 20,000, so it will make your switch 16,000. And then your lab partner goes on his switch and he notices that he's not the root anymore, and he types spanning tree VLAN 1 root primary, and now he will be made 12,000, and so on until you both get to 0, and then it'll be back MAC address. Now the reason why this is important is because the spanning tree VLAN 1 root primary command is dynamic. It goes out there, listens, figures out who the current root is, and beats it. However, spanning tree VLAN 1 root secondary is the exact opposite. Spanning tree VLAN 1 root secondary is hard-coded to 28,672. Therefore, there'll be a question in the exam. Look for it. The question in the exam says, I've got 3 switches that are factory default, and I've just typed this command, spanning tree VLAN 1 root secondary. What has actually happened? What's happened is you've set that value to 28,000, which is now beating the others because the others are all on default. So if everything's set to factory default and you take spanning tree VLAN 1 root secondary, that will actually make this switch the root. So recap. Spanning tree VLAN 1 root primary is dynamic. It will change and search for the current root and beat it. Spanning tree VLAN 1 root secondary is hard-coded and fixed and will only ever set the value to 28,000. So let's do a quick quiz. So we've got 4096 000D BD68 E756 versus 32,768 000D BD68 001. Let's have a look at the winner, the left or the right. Who do you think is going to win? It's the left. In this instance, the priority is just you can't beat that. So now we've got left and right, same priority. So now we have to look at the MAC addresses closely. Who has the lower MAC address? In this instance, it's the one on the right. Now we've got the same priority, 2 different MAC addresses again. Who has got the better MAC address? The one on the right. Same priority. Who has the better MAC address? Got to look at the whole MAC address. A lot of you hopefully said it's the one on the right. But look, BD38 as opposed to BD68. The whole MAC address. And last but not least, this one, priority. Different priority, so the better priority is going to be the winner. Now the spanning algorithm path cost was, spanning tree was written when Ethernet was 10 meg and they thought that 10 meg was the fastest thing in the world. Are you crazy? This is amazing. However, over time we've gone to 100 meg. We've gone to a gig, we've gone to 10 gig, we've gone to 40 gig, we've gone to 100 gig. So the actual numerical values for the path cost have had to change and evolve over time. Now, even this slide is out of date because now you go to some of the switches and you do show spanning tree and they'll be in the thousands. Like a gigabit link will be 200,000. A 10 gig link will be 20,000. A 100 gig link will be 2,000. You know, they've exploded those numbers. So when you do these labs, do these few show commands to check the path cost. So in this example, from switch 2 to switch 3 via switch 1, going towards the right directly has a less path cost than going via switch 3 because it's cumulative. Because we've got 19 plus 19, whereas the one way is just 19. So that's another thing to remember. Your spanning tree, that's the way to make sure there's no loops. All the path costs are cumulative. They have to add up. And that's the way that's why we avoid having loops. Path cost is cumulative. Different types of spanning tree. Like all good standards, there's lots of them. So the original spanning tree was just called spanning tree. And then Cisco came up with per VLAN spanning tree. So you got 10 VLANs, you got 10 different instances of spanning tree. However, there's some timers which we'll get into in a minute. Now, rapid spanning tree came along and they said, look, normal spanning tree is too slow. Let's have rapid spanning tree. And then Cisco said, all right, fine. Let's have rapid per VLAN spanning tree. And then there's a compromise overall multiple spanning tree. The biggest difference between per VLAN, rapid spanning tree, one spanning tree instance for all the VLANs. Per VLAN spanning tree, both rapid and normal, one spanning tree instance for each VLAN. You got 10 VLANs, you got 10 lots of spanning tree. So the compromise was multiple spanning tree. So let's say you got 50 VLANs, group them up into blocks of 10 or 15 that make sense, and say those blocks are now groups of spanning tree. So you might only need 4 or 5 instances of spanning tree. Now the states. This is the very interesting part about the states. The numbers aren't on here, so unfortunately just write these down as I talk. Blocking, listening, learning, forwarding, disabled. So when spanning tree is disabled, then it's not doing anything. So blocking, learning, listening, forwarding are the ones we care about. If a port is currently blocking and it either no longer receives BPDUs or it receives BPDUs that are superior, it will stay in blocking for 20 seconds. 20 seconds. Maybe I'll try and write it on here. Give me one sec. Pointer, pen. 20 seconds. Wow, this is terrible. Never mind. Now, after 20 seconds have gone past and it hasn't either learned something better or learned anything new, then it will go into listening. It will stay in listening for 15 seconds. What it's doing there is it's listening for BPDUs. Listening is listening for BPDUs. Once it's spent 15 seconds making sure that all the BPDUs it needs to know, then it starts learning. What is it learning? It's learning MAC addresses. And it stays in the learning state for another 15 seconds. Why is this significant? This is significant for 2 reasons. Oh, and once it's learned all the MAC addresses, bang, forwarding straight away. Why is this significant? Because there are 2 questions in the chapter exam. One question will be, if a port is currently blocking, how long could it take to begin forwarding? 20 plus 15 plus 15. The answer to that question is 50 seconds. Another question on the exam might read, I've just plugged in a cable to my computer. What is the maximum time you expect before the port begins forwarding? Well then, that's just coming up. So that's 15 plus 15. So that's 30 seconds. So if a port is currently blocking, it can take up to 50 seconds. If it is just plug it in, so it goes learning, listening, that's 30 seconds. Now, a few lessons ago, we looked at a command called spanning tree PortFast. Spanning tree PortFast is a fantastic command because all it's done is it says, right, we're still going to run spanning tree, but we're going to take the learning time the listening time and the learning time, and we're going to drop those timers down to 0. So therefore you plug your Windows PC in and we go listening, learning, forwarding. So therefore your Windows box is so fast now that it can't afford to wait 30 seconds. It'll just give up. So 20 seconds of blocking, 15 seconds of listening for BPDUs, 15 seconds to learn MAC addresses. But the spanning tree PortFast command sets those 2. So PVST is actually a pretty cool way, and both PVST and MST you can do this, because you go to your boss and say, right boss, we need to buy 7 or 8 100 gigabit connections that are going to cost $2,000 each. And it says, oh, that's fine, you know. So what sort of bandwidth are we going to get? Well, because it's spanning tree, we'll only use half of them, because the other half are redundancy. Your boss is going to say, no, not wasting that sort of money. So what you can do is you can trick it. You can say, all right, let's set it up our VLANs, either PVST or MST, so that VLANs 10 and 20, so VLAN 20 is forwarding this path, because this is the route for 20. And VLAN 10 is forwarding on this path, because this is the route for VLAN 10. So therefore both of our expensive uplink connections are now in use. So all these users down here on VLAN 20 still get there. So VLAN 20 come along and go zoop over to here, and then VLAN 10 come along and go zoop up to here and come over to here. Now, it's still spanning tree, it's still redundancy. So if this link is unplugged, after a few seconds, depending on if it's rapid or normal, then both VLANs will go on the other one. So we have our redundancy. It's like a sort of a load balancing but it's sort of load sharing. Because load balancing is equal, load sharing is unequal. So if you've got a lot of people on VLAN 10 and only a few people on VLAN 20, then everyone on VLAN 10 still has to fight over here, and everyone on VLAN 20 still has to fight over here. But it still frees up bandwidth that you otherwise wouldn't have had. So just a few more extra commands about PortFast and BPDU guard. I've already talked about PortFast. PortFast goes from blocking to forwarding almost immediately. I should say almost immediately. So the learning and listening are dropped to 0. Really useful for PCs. But there's also such a thing as BPDU guard, which is super, super awesome to help you stop loops in your network. It's really, really cool. Because what makes BPDUs? Switches. So therefore, if these PCs, so for example here, this switch here, I've just got a cable out of one port into the other port. Bang. There's a loop. If without BPDU guard on spanning tree, this switch would die. So because there's too much traffic just whizzing around in this little loop. But now we say, okay, BPDU guard. So this is a PC. A computer is never going to generate a BPDU. So if this port 11, 18 and 6, if they ever receive a BPDU, that means someone's done something silly like this. So bang, instantly shut down that port. And as we know, BPDUs are sent every 2 seconds. And that's why we have this warning when we turn on PortFast. You know, this can cause loops because the timers are 0. So we have to wait 2 seconds for the BPDU and then we can do it. So this is a really great command, spanning tree BPDU enable. Now, in the material, I will say one thing that I don't like. They say put spanning tree BPDU on all your ports. So you got spanning tree PortFast, and so you got 2 lines. So that's a lot of extra text to type. But right at the very top, you can actually say spanning tree PortFast BPDU default. And therefore, every port that you enable PortFast has also been enabled for BPDU guard as well. So just a bit less typing. That's pretty cool. So PortFast negates the timers. BPDU guard stops the loop. As soon as you receive a BPDU, it shuts down the. And that's the end. Thank you for watching. See you next time.